So we all know from complexity theory that there's a lot of evidence showing that randomness should not help us solving more problems in polynomial time. So in particular, for instance, in this work by Nizam and Wiggerson, they show that if a hard function exists, then you can build a pseudo-random generator, and in this case, you have that P is equal to BPP. And this shows a nice trade-off between two objects that seem unrelated, like hard functions and randomness. And in this setting, it's not even known if the non-deterministic version of these two complexity classes are equal or not. So in particular, we don't know if MA equals NP. And despite a lot of effort and a lot of beautiful work in this line, this question is still wide open, and this is the main focus of this work. So let me quickly recap about NP and MA. So the complexity class NP is defined by requiring some polynomial time deterministic verifier D that receives two inputs. One, the instance to the problem, and Y, that's a proof that will help this deterministic algorithm to accept, to decide the language. And we require that for yes instances, there must exist a proof Y that makes this algorithm to accept. And for no instances, no matter what proof is given to this deterministic algorithm, it should reject. And in MA, we have the same setting, but now we allow this verification algorithm to be randomized. And we require that for yes instances, there is a proof that always makes this verification algorithm to accept. But for no instances, no matter which proof is given, with high probability this algorithm rejects. And as I said, this NP is believed to be equal to MA. And very informally, our results shows that if some sort of quantum PCP conjecture is true, actually this is equivalent that MA equals NP. Okay, and this some sort of quantum PCP conjecture, we call it Stoquastic PCP conjecture, and you see it later why the name. And looking at it through the same lens as hardness versus randomness paper, this shows a nice trade-off between two seemingly unrelated objects, as quantum PCPs and random coins. And we can see this from two different perspectives. So on the good side, we might be closer to solve MA versus NP. But this also shows that PCP, even if quantum PCPs, the quantum PCP conjecture is true, it should be very hard to prove because otherwise you should be solving this long-standing open problem. And in order to describe a bit better what this conjecture is, I have to mention one of the main objects of Hamiltonian complexity, and this is the local Hamiltonian problem. And this problem is a quantum version of CSPs, and an input to this problem is M local Hamiltonians, and you can see this as M quantum clauses. And you want to decide if there is a quantum state that has low energy, according to this Hamiltonian, or in a more classical language, if there is a quantum assignment that has a quantum unset value that's low, or no matter which quantum state you take, it has high energy, according to this Hamiltonian. To be a bit more precise to non-quantum people, local Hamiltonians, they're just Hermitian matrices, and you can think of them as projectors. And what we're considering is just what's the Ismail's eigenvalue of the sum of these local terms. And what we are interested in here is understanding how hard this problem is. And the hardness of this problem, of course, is related to how beta and alpha they compare to each other. And Kitaev showed 20 years ago that if beta minus alpha is some inverse polynomial, then this problem is also QMA complete, proving the quantum Cook-Levin theorem. And then we might ask, what happens if beta minus alpha is a constant? And this is the quantum PCP conjecture states that this problem is still QMA hard. But it's still an open problem if such a quantum PCP conjecture is true or not. So we have two extreme cases. On one hand, we have CSPs that are classical Hamiltonians. On the other extreme, we have fully quantum Hamiltonians. But we can start looking what's there in between them two. And we can start looking less quantum Hamiltonians. And one of such Hamiltonians are also called stochastic Hamiltonians. And they are defined by asking, so you have this local term, hi, and this local term has eigenspaces. And you look to the eigenspace with the smallest eigenvalue, and a Hamiltonian is stochastic if this eigenspace associated with the smallest eigenvalue can be described as a sum of rank 1 projectors, where every one of these projectors is spanned by a state with only non-negative amplitudes. Okay? So this is a generalization, this is a restriction of Hamiltonians, because on a general Hamiltonian this is true, but allowing phi ij's here to be anything, have any arbitrary complex phase. And one very important consequence of these stochastic Hamiltonians is that the state that has low energy, or the eigenstate with associated with the smallest eigenvalue, there is such an eigenstate that has only non-negative amplitudes. So that's why these Hamiltonians are called stochastic, because in some sense, these amplitudes can be just seen as a probability distribution, because there's no choice of phase, nor no choice of minus or complex phases. And in this talk, we restrict even more these Hamiltonians, and we ask these phi ij's, like these rank 1 projectors, to be spanned by states that are uniform superposition for bit strings. So in other words, these states are actually just a description of a subset. So you have a subset of strings, and once you fix that, the amplitude is already defined. And given this definition of stochastic Hamiltonians, you can go back to our problem and ask, how hard is the problem of deciding a stochastic Hamiltonian? So now you're given the promise that these local terms have this extra property, and we want know if the smallest eigenvalue is exactly 0, so it's a somewhat simpler problem than before, or if it is above some beta m for all quantum states psi. And again, we ask, how hard is this problem? And Brav and Hall, they showed roughly 10 years ago that if beta is some inverse polynomial, then this problem is MA complete. And first, this is very surprising, because this is the very first natural MA complete problem. And it comes from quantum computing. So it shows some tight connection between these two fields. And our work shows that if beta is actually a constant, then actually this problem is NP. We can de-randomize the result of Brav and Hall for this regime. And for the rest of this talk, I'll try to make this connection between Hamiltonian complexity and the randomization a bit more explicit. And then I'll go further to explain a bit how Brav and Hall show that stochastic Hamiltonians is included in MA, and then show roughly a proof sketch of how we de-randomize the result, and finish some comments on open problems. So let me put our result and theirs side by side. So the only difference is that in their case, they have an inverse polynomial promise gap. And in our case, you have a constant promise gap. And if you're from complexity theory, you have seen this before. And where? In the Pcp Theorem. So a corollary from these two results is if there is a gap amplification procedure, as Dinur did for classical CSPs, but now for stochastic local Hamiltonians, then MA equals NP. Okay, so the idea is that given this MA hard problem, you can just gap amplify it and then solve in NP. And that's what we call stochastic PCP conjecture, this gap amplification procedure for stochastic Hamiltonians. And how big is this assumption? Actually, not so much, because this is equivalent actually to proof de-randomization. Because if MA equals NP, by the Pcp theorem, there is the stochastic PCP conjecture is also true. Okay. So let me try to explain a bit now how Brav and Hall show that this stochastic Hamiltonians with inverse polynomial gap is actually in MA. For that, Brav and Hall, they define an implicit graph Why is it implicit? Because it has exponentially number of vertices, so every bit string is a node in this vertex. And two strings are connected if they appear in the same ground state of the Hamiltonian. So let's see an example that I hope it helps. So let's assume that we have a 3-qubit system. So n equals 3. So all the nodes of our graph are all the 3-bit strings. And let's look, for instance, the string 0, 0, 0 and 0, 0, 0 and 1, 1, 0. So we have that 0, 0 and 1, 1. They appear in the same ground state of P1, 2. In this case, by fixing the third bit and flipping 0, 0 to 1, 1, we'll add some edge here. So this edge is corresponding to this requirement of how we connect it. And on top of that, Brav and Terhall, they define a notion of bad strings. And they say that a string is bad if it does not appear in the local ground state of some Hamiltonian. So again, in our example, the string 101 is bad because when you look to the first and the third bits, 1, 1, it does not appear in the ground state of P1, 3. So in this case, this string is bad for P1, 3, and in more general, we say that it's bad for the whole Hamiltonian. Okay? Given these definitions, the MA verification procedure of Brav and Terhall is the following. So the prover, let's assume that, that the Hamiltonian is, let's suppose that the Hamiltonian is frustration-free. So the prover should send some string that is in the ground state of such a Hamiltonian. And the verifier just performs a random walk on the previous graph for polynomially many steps. And if at some point, this verifier found a bad string, the verifier rejects. And what Brav and Terhall show is that if the Hamiltonian is indeed frustration-free, then any string in the ground state of this Hamiltonian, like if you consider the connected component of this string, it only contains good strings. So no matter how long you do a random walk, you never find a bad string in this case, and you never reject. On the other hand, if the Hamiltonian is inverse polynomial frustrated, if the unset value is inverse polynomial, then one can show that there are a lot of bad strings, and on top of that, the graph is a good expander, is a somewhat good expander. So in this sense, if you do a random walk, you find such a bad string with high probability. Okay, and with this theorem, then they show that stochastic Hamiltonians are in MA. And in our result, our technical lemma is actually showing that if the Hamiltonian is very frustrated, namely it's constantly frustrated, then for every string in the graph, there is a bad string that's close to it. Okay, that's in a constant radius ball around it. So from this technical lemma, it's not hard to see that this gapped version of uniform stochastic Hamiltonians in NP, because the prover just provides the string that's supposed to be in the ground state of the Hamiltonian. The verifier just brute force search for a bad string on its neighborhood. And if it's a yes instance, from the same argument as Brav and Terhall did in their completeness case, the verifier never finds a bad string if the Hamiltonian is frustration-free. But from our technical lemma, we show that if indeed the Hamiltonian is very frustrated, then he will always find a bad string, and in this case, the verifier rejects it with probability 1. And for the rest of the talk, now I'll try to give a bit of intuition how we prove this theorem. And the main idea is that if you have some state S, let's say that S is a candidate of the ground state of the Hamiltonian, but there is some term of the Hamiltonian that's highly frustrated by this quantum state. Then what we show is that if you project S onto the ground state projector of HI, that actually adds a lot of strings to this state. Because since it's stochastic, whenever you apply this projection, it only adds strings. And then we can augment this idea, and what we show is that you can always find non-overlapping set of projectors and apply on these candidate ground states. And this makes the number of strings increase a lot. And if you repeat this a constant many times, then we must have found a state that contains a bad string. Once you have this constant depth non-overlapping projectors, we can use some light cone argument to actually retrieve the constant size path. So let me try to explain a bit more details. So let's assume that that the prover sends some string x1, and that's our current candidate for the ground state of the Hamiltonian. But the Hamiltonian is very frustrated. So either the string is bad, in which case we're done, or what we show is that we can find a lot of projectors that are no overlapping, and then we can apply these projections and find some quantum state S2. And what we show is that the support of S2 has exponentially more strings than this single string here. And we can ask ourselves again, does this state contain a bad string? If it does, we are done. Or again, we can repeat this process and every time add exponentially more strings to this state. So at some point, after constantly many steps, we have to have reached all strings. And if you have all strings, we must have a bad string because we assume that this Hamiltonian is highly frustrated. The second part of the proof is, let's assume that you have this constant depth circuit that finds some state that contains a bad string. And if you remember the definition of a bad string, it's bad because it's bad for one term. So we can consider the bad sector of that string. And then we can consider all of the projectors that affect this position. In particular, you see the light cone of this bad sector onto the original string. And we can safely remove everything that's outside of this light cone because we are sure that this does not interfere on the badness of some string. So of course, the state that you have here is different from before because we removed some projections, but we have the guarantee that there exists a bad string in this last layer. And since there are constantly many steps here, the depth is constant, then the number of projectors is also constant. And in this case, we can show that there exists this constant size path from X to the bad string here. And this is the big overview of our proof. We can actually show a few more results. So we can actually show that if this Stochastic PCP has actually a bit more properties, we can normalize not only MA, but also RP. So we can show that randomness does not help in one-sided error. We also prove a slightly stronger result, and we show that instead of deciding if the Hamiltonian is slightly frustrated or constantly frustrated, so before it was zero against constant, now it's negligible against constant. And this problem is still in NP. And finally, one thing at some point we realized that actually we can forget about quantum. We can define a classical problem that only involves sets of strings. And we call this problem set CSPs. These are a set generalization of normal CSPs. And we show that this problem is MA hard, actually MA complete, if you have inverse polynomial gap. And we can show that this problem is still in NP if the gap is constant. And we think that, these proofs are actually redoing the proofs that we have in these previous works. But we think that conceptually is very important for the field of classical complexity theory to be able to study this problem of the randomization and PCPs without diving into quantum computation. And hopefully this will be online soon. And let me just finish with some open problems. So I think the main open problem that is triggered by our result, can you prove or disprove this stochastic PCP conjecture? In our proof, we really need that the stochastic Hamiltonian is uniform. So we have this restriction that there's no different amplitudes between two strings. And we think that trying to improve this to the non-uniform case, even if for complexity theory does not have many more implications, we think that we could understand better Hamiltonians from this case. And finally, Brav and Terhal, in their result, they use their techniques to show that how to classically simulate adiabatic computation, adiabatic evolution of stochastic Hamiltonians. And we wonder if our results somehow but they show it only for the frustration-free case. And we wonder if our result could also make us extend it to the more general case. And this problem is very important because, for instance, D-wave machines, they perform exactly a adiabatic evolution of stochastic Hamiltonians. So this could help us understanding a bit more D-wave machines. And thank you for your attention. So the point is, we don't. But I think the point is we don't prove stochastic PCP. We don't prove stochastic PCP. So I think in stochastic PCP, a pseudo-random generator must be somewhere there, right?
But do you think it's necessarily will also prove lower bands?
No, I think if you prove MA equals NP, this proves. I think this shows circular bounds, and I think there are people in this room that could answer these better than I do. So yeah. So.